Good morning and welcome back. I've learned recently that we already have day 9 of this course, so 2 days to go. Yesterday we started with the topic how to assess safety issues dealing with combustibles, and we ended with introducing safety characteristic data. So these are quantities we need to address the properties of the combustibles with respect to safety. So as I've said, there are no material constants, so like boiling point, and they are not independent from the determination method. So you can find in literature different values depending on the method they have used and so on. But they give us quantitative information about material properties, and I have shown you yesterday with the explosion groups. We can use this concept also for the so-called gas groups. So for the chemical and petrochemical industry, we separate all the combustibles we have, and we have thousands of them, into 3 groups: 2A, 2B, 2C. And the proper equipment we want to buy to consider safety is focused on the group we need. So group 2A, propane, large minimum ignition energy, large maximum experimental safe gap. Okay, here the safety requirements are not so high concerning the electrical equipment we want to use, compared to 2C, hydrogen, acetylene, substances which are very easily to be ignited, and therefore here the requirement concerning the equipment are much higher. But okay, again, we have 3 groups, and all of our substances we put into these 3 groups based on the safety characteristic data. That's the idea of this concept. So we have several safety characteristic data. I will introduce only the most important one here. And the main idea is to quantify explosive mixtures, then to quantify the ignitability of the substance, and to quantify the effects of an explosion. And first of all, again, it's to compare different combustibles with respect to safety. And if you know that the measures you have taken for other combustibles in the same group are valid, you can use these measures also in this gas group, explosion group, for other combustibles. So that's the idea. And we have here again these 3 main categories, and now we will go into some details here. So explosion limits, or in the American literature also preferred to use flammability limits. So these are normally the same. Refer to the limit value of the fuel content at which no independent flame propagation occurs in the mixture. This can be determined by different standardized measurement methods. So there is the ASTM E681-98. They have an optical criterion. In Europe we have 2 methods based on this standard here, EN 1839. We have a tube method where we have an optical criteria, and we have a bomb method with a pressure criteria. Here we have normally to check, is there a pressure rise of 5%? So we have a closed vessel, ignite the mixture in the center of the vessel, and test, I think in 1 of 10 experiments, or maybe only in 1 of 3 experiments, an ignition. Of course, there has to be an ignition, and this can be seen then with the subsequent combustion process when we look at the pressure curve. So if there is a pressure rise of 5%, we consider this mixture as combustible. In the optical methods, there are different criteria leading to different limits. So here we have an electrical ignition source. The tube here is filled with the combustible mixture of interest, and we ignite here with very strong spark. So the energy is in the range of joule. The mixture, and in the US, it's required that the flame reach the top of the tube. In Europe, it's only required that the flame leaves the area of the spark, so that flame can propagate for a given distance and then extinguish, but this would be considered as flammable in Europe and as not flammable in the US. Therefore, we have different values. But for a methane, it's 4.4% lower flammability limit in Europe and 5% in the US. So it's not very important issue, but you have to consider this if you compare literature value. There are differences. And again, flame propagation in 1 of, I think, 10 experiments. I have to check the standard here again. So there's some probability behind this too. And a lot of experiments, because you have to change your mixture composition, perform the experiments. If you have a mixture which you classify as flammable, you have to reduce the amount of combustible near the lower flammability limit, perform the experiments again. So there's a lot of work behind it, and it's at least in Germany, it's frustrating work because you're sitting all day in a dark lab and looking at such a tube. So there is no proper method how to automate it yet using optical sensors. So the eye and human factor is here better than any artificial intelligence at the moment. So if we add nitrogen to our mixture, we of course can influence the explosion range. So here we have the limits using the European standard, 4.4 and 17.2% of methane in air. These are the values in air, and then if we add additional nitrogen to the air we have, you can see the lower flammability limit is nearly not influenced, but the upper flammability limit is decreasing. So stoichiometry starts at 9.5, is following around this line. So of course, when we add nitrogen, we add an additional heat sink here, and therefore the explosion range gets smaller. So when we look here at the numbers of the plot, we always have a non-flammable region for most of the substances below the lower flammability limit, and we have a non-flammable region above the upper explosion limit or upper flammability limit. So these mixtures are too lean or rich, and a self-sustaining flame front propagation is not possible. Again, we deposit very strong spark, but you can also use chemical igniters. So it does not depend on the ignition source. The energy release from the chemically stored energy heating up the system is not enough in this mixture that there is no self-sustaining flame propagation. When we use methane oxygen, you can see if there is no nitrogen, we have a much broader range. So from 4.4 to up to 66 volume percent of oxygen. So of course, if you have to deal with combustible oxygen mixtures, you always have to be very, very careful. So there were severe experiments, accidents when you have oxygen atmospheres, pure oxygen atmospheres. It's really difficult to handle, and concerning safety, mixtures of combustibles with pure oxygen, are quite difficult to handle. But okay, you see the same effect. There is a lower and an upper explosion limit. And when we compare here different combustibles, you can see there's a quite huge difference. And here we consider, of course, volume percent. So the large hydrocarbons here, N-hexane and N-heptane, have a very small combustible region, around 1 to 9%, 1 to 7%, 0.7 to 6%. But of course, we have quite large molecules which consume a lot of oxygen. Therefore, this small range here, molecules like hydrogen or carbon monoxide, you see, have a very broad range. So from 4 to 77%. And here this carbon monoxide, I think this is dry carbon monoxide. As we have discussed in the kinetics part, if there are traces of hydrogen, traces like water, we could have also a lower flammability limit here. But okay, you can find these data tabulated in specific databases, and most often you do not have to measure them for yourself. And the safety concept is normally, one of the safety concepts is normally to stay quite below the lower flammability limit or lower explosion limit. So as I said yesterday, in our labs we have sensors, gas sensors measuring the quantities of combustibles, and I think depends on the sensor, but I think we're talking about maximum 10% of the lower flammability limit. So if there is a mixture of with 0.4% hydrogen in air in our lab, the system already starts to warn us and eventually shut down all electrical power supply. So they are quite below this value, and therefore it's not so important to know this value precisely. So as I've said, we have difference in methane, 4.4 in Europe, 5% in the US, but 10% of this value is also a quite small value. So with respect to safety, it's okay to have differences, and as I said, this depends on the methods we are using. So why do we see flammability limits at all? So so when we look at, for example, the flame velocity, laminar burning velocity here, propane in air, we can see, okay, near the stoichiometric mixture where we have the optimum composition with request to or consider with respect to combustion, we see the highest flame velocity here around 60 centimeters per second. And if we go to leaner or richer mixtures, the energy release per volume decreases, and therefore the temperature goes down and the velocity goes down. So this is something we can explain. But when we look at adiabatic flames, there is still a heat release for a broad range here. So from the point of view of combustion, there is still energy release. So it should be possible theoretically to see a flame propagation. But we are here on Earth. We have to deal, for example, with gravity. And you see here we have at the flammability limits, explosion limits, 4.4, and here 10 points, around 2%, around 10 point something percent. We have very low flame velocities. It means these flames can be ignited, and then they so you create a core of hot gas, and then we have something like buoyancy. So we have buoyancy, the flame is propagating upwards due to buoyancy and tries to burn the unburned mixture. However, so below 10 centimeters, buoyancy is very important for flame propagation. And so you create a flow field which disturbs our flame propagation, and therefore quenching can be observed. So the flame is maybe ignited, but it will quench after a short period of time. Depending on the criteria you have. So in the US, as I've said, the flame has to reach the upper end of the tube, so it needs a higher flame velocity. That means a slightly richer mixture compared to the European method. And these are different energy loss processes. Also radiation is here very important. So in stoichiometric flame also loses energy due to radiation, but it contributes here only with some percentage to the total energy balance. Here it's very important at these very slow flames, and has to be considered. As I've said, the method is an important factor. Move to this side. So as I said, it depends on the method you use, and of course this plot is not a scientific plot, so the methane flammability limits do not change with time. Here it's not better. Okay. But of course, there were several different experiments with different criteria, and therefore you can see a broad variety of final results. It means if you look into literature, you find different numbers, and there is no exact number. It depends always on the method. Each of these values is a correct value depending on the method they have used. How do these flammability limits, explosion limits behave, change with temperature or pressure? So with pressure, it's quite difficult. So for most hydrocarbons, it's broadening. So the lower flammability limit is nearly not influenced if you go to higher pressures. And the upper flammability limit going to richer mixtures. But here you have to be careful. It's a kinetic effect, and it depends strongly on the combustible you consider. So it's not a rule of thumb. So for most hydrocarbons, it's correct, but always you have to check carefully, is it correct for your combustible you use. There are also combustibles where the flammability range is decreasing or getting smaller. And this is a kinetic effect. With the temperature, it's more easy to describe. If you increase the initial temperature, you always increase the flame velocity. And therefore, the range is broadening here. So an increase of temperature means that you have lower flammability limits and higher upper flammability limits. So there are some further data which are more important for the colleagues in chemical industry. Maybe you can find this maximum oxygen content. So this is a tangent to the explosion range parallel to the axis with 0% volume oxygen. And there is a maximum proportion of combustible and minimum proportion of inert gas. I have put them here just to complete the overview. So if we look again at such a ternary diagram of combustible nitrogen and oxygen. So here this is the explosion range. Here are the limits in air. So the limit in oxygen concentration is parallel to this axis. So here we hit the explosion range, and the idea is this: when I know this value, I just have to take care that in my lab, in my chemical plant, I always stay on this side. Then I never ever get an explosive mixture. Therefore, if I know this quantity, I can optimize my safety measures with this quantity. The same concept we have with how is it called again? Maximum proportion of combustibles. So if I stay below this line, I'm always in a safe area, and with the minimum amount of inert gas, the same. So therefore, you can also find tabulated this value. And again, the idea is I have to know this. So where are my mixtures flammable? And then I can get measures to stay outside this explosion range. So when we consider liquids, there's an additional effect, and this is the vapor pressure. So I think flashpoint will be explained later in this part of the lecture. But if you have a flammability and you increase the temperature, you increase the vapor pressure. And flashpoint means you ignite the gas atmosphere above your liquid phase and check, is there a stable flame on top of this liquid phase. And this of course depends on temperature or vapor pressure. The higher the pressure, the more combustible gas you have above the liquid surface. The explosion point here is slightly smaller. This corresponds to the lower explosion limit. That means here the vapor pressure gives us already a combustible mixture. However, when we are above a liquid surface, we cannot ignite it because the disturbance from the liquid surface is too big. And then if we increase the temperature and vapor pressure again, we finally reach this upper explosion point, which corresponds to the upper explosion limit. So sometimes in literature also these quantities are given, upper and lower explosion point. Okay, so why do we need this flash point? That means the minimum temperature at which we can see a stable flame on our liquid phase. Okay, so first of all, it's approximately in most cases 5K above the lower explosion point. That means at the point where we reach the lower explosion limit. And this is mainly used for classification of flammable liquids. So we have a globally harmonized standard for dangerous goods. And when we follow this, we have several hazard categories here, hazard classes. So one of the hazard classes is flammable liquids. And here we have different categories. And you see if we have a flash point below 23 degrees Celsius, typical ambient atmosphere, at least in Europe, and a boiling point below 35%. Then this is then flammable liquid of category 1. So this is the most dangerous category. If we have a higher boiling point, we have category 2. If we have also a higher flash point, so above 23 degrees Celsius and below 60 degrees Celsius, we have a flammable limit of category 3. There's also in the globally harmonized standard here an fourth category, so above 60, below 93 degrees Celsius, which is, for example, used in the US. This is not valid in Europe, or not used. But this is the main usage of this safety characteristic data flash point. So auto-ignition temperature. As we have seen with hydrogen, thank you. As we have seen with hydrogen, when we have looked at this PT diagram concerning the ignition limits, there's always a criteria at which temperature in a closed vessel we can ignite our mixture without an additional heat source. So that means we have an closed vessel and heat up the outer walls, therefore heating up the gas phase, and at a specific temperature these systems will ignite. And you see it here for ethanol, the ignition temperature here is 425 degrees Celsius, which is of course much higher than the flash point. So here the ignition source is the hot temperature of the surface. Here the ignition source is normally a lighter which ignites the mixture above our liquid phase. There are some influences, of course. We are talking about the ignition in a closed vessel. So we have to consider the material of the vessel and the surface properties of the vessel, and the area of the ignition source. I don't have an image here, but for liquids, for example, we have an specific glass flask in a heated oven, and we drop some droplets of the liquid into this glass flask and look from the top, do we see a flame or not? So inside this glass flask we have a broad mixture range from very lean to very rich mixtures, and we can then see an ignition. But of course we do not precisely know at which mixture the ignition mixture composition the ignition has started. So it's quite easy experimental methods, which is also standardized. But of course, we do not get all the details from the experiments. So the quantity minimum ignition energy we have discussed already in detail. So that's the minimum energy stored in a capacitor, and the energy is then calculated 1/2 C U square. U is then the breakthrough voltage. So what we have to consider is, if we have a combustible in air, the ignition depends not only on this energy. We will discuss it later in this lecture more in detail. So we find only the energy value, but it depends on the shape of the electrodes, the electrode distance, the mixture composition. But nevertheless, we have this value, and it's a very helpful value because it's one of the possibilities to classify our substances into these three groups. Example again, ammonia, 40 millijoule. Okay, we are explosion group 2A, and all safety measures we want to use should fulfill the requirements for this explosion group. We don't have to buy the expensive measures for group 2C, for example. This we will discuss later on in detail. The typical experimental method is a so-called Hartmann tube. So we fill this glass tube with the combustible air mixtures we want to examine, and check if there is an ignition with our energy, yes or no. And again, in 1 of 100 experiments. So normally you do not replace for each experiment the gas mixture if there is no ignition. So you place it normally after 10 experiments. So it's a quite fast process, but nevertheless it takes a lot of time. So and if there is an ignition, here there is it's not a closed vessel, so this here will open, the pressure relieves, it will fall back, we can flush our test vessel and perform the next experiment. So we need a huge number of experiments, but this could be done quite fast. So why we need a huge number of experiments? So we are talking about the minimum ignition energy, the absolute minimum value to ignite a mixture of hydrogen and air. And hydrogen is in the range of 4 to 77 volume percent flammable, based on these data. So where we have the minimum value, so we have to measure the energy necessary for ignition along the whole mixture composition range. And here we find then, okay, the minimum value of 17 microjoule is in the range of 22 volume percent. And of course this is different for each combustible we have. So we have to perform a lot of experiments finally to find this value precisely. Still in German, so now I can test your German. We have the MESG value in German Normspaltweite, and this is the largest gap widths where we can see a flame transmission in a given experimental setup. And just to explain it in detail, I have prepared this video here. So we have two chambers, chamber 1, chamber 2, connected by a nozzle here, circular tubes, and this one is a little bit bigger, the lower one. And we then ignite both mixtures here on the left, and let's try if the video is working. So the flames are coming from the left. You see slow flame propagation, and when you see here already the hot gas is sucked into the tube here, into the pipe here, as there is of course a pressure difference between the two chambers. The gas is accelerated along this tube, and but what you also see is, if we have the slightly larger tube here, there is a flame transmission. In case of the smaller tube, we see here some chemiluminescence, but the flame is finally quenched here in the system, and so no flame transmission occurs. On this we will discuss tomorrow more in detail what are the effects, the reasons why we can see a flame quenching using, for example, flame arresters. This also depends on the mixture composition for the different combustibles here: propane, ethylene, and hydrogen again. So here we are around 27.5 volume percent where we find the minimum. So these values are mostly near the stoichiometric mixture composition. And of course these quantities depend from temperature. If we increase the temperature, the maximum experimental safe gap reduces. So of course hotter temperatures are more easy to ignite. If we increase the pressure, we also reduce the experimental safe gap, so it's more or less a linear correlation here. Here is 1 over P. So higher pressure means smaller experimental safe gap. So this is of course an issue if you have to consider safety assessment for your equipment. We have seen it yesterday with the example of hydrogen, where I've explained to you that there is a company responsible for safety assessment, which has written on their homepage, or on their homepage, hydrogen does not explode below 18%. This is of course not correct. Maybe they have used these detonation limits. So a lot of mixtures have detonation limits. That means under proper conditions. And this means normally, for example, a long closed pipe. So seldom we can see detonations in a room like this. Eventually hydrogen, as we have seen yesterday, the length or the distance hydrogen is only in the range of several centimeters. So each share here produces a lot of turbulence, which may then lead to detonation in case of hydrogen. But for the most other hydrocarbons especially, this detonation occurs only when we have proper conditions That means normally pipe diameter, mixture composition, temperature, and pressure. And here we see an example for propane. So we have an 18-meter long pipe with a given diameter, with a given mixture composition, and you see that the flame accelerates over 6 meters until we finally reach the detonation. So at that time the flame propagates then with more than 2,000 meters per second through our system with much higher pressure than the typical explosion pressure. So normally we try to stay in the deflagrative region to avoid detonations, and as I said, in open configurations this normally does not occur. There are seldom accidents like Buncefield disaster where it is considered that there was a detonation, but for most hydrocarbons, especially in open configurations, we would not see a detonation. So we have to consider mainly the explosion pressure also for deflagrative situations, and this is an important quantity. So here you see, for example, the explosion pressure as a function of time for hydrogen, methane, and ammonia. So hydrogen burns very fast, so we have a very fast pressure rise, reaching here a pressure in the range of 7 point something bar, and then it cools down, the pressure decreases. Methane burns slower but reaches a higher explosion pressure. The flame temperature is here maybe more or less the same. I think it's slightly higher for methane. And we also have to consider if we burn hydrogen, so H2 plus half oxygen gives water, so we reduce the number of moles in our system. In case of methane, methane plus oxygen gives water plus CO2. This is not the case. So this is also the reason why we have slightly higher pressure here in case of methane. And in case of ammonia, ammonia flames are very slow, normally in the range of 6.5 centimeters per second. Again, buoyancy dominated, so when we see an ammonia flame in a large cylindrical vessel, we see a flame which goes up, hits the upper wall, and then goes down at the side. So of course here cooling effects are very important, and so even though that an ammonia flame has an adiabatic flame temperature above 2000 Kelvin, we measure much lower explosion pressures because here the cooling effects are dominating the system. But normally we do not want to know all the details. So first of all, why is there an explosion pressure? So the explosion pressure depends on our initial conditions and on the final flame temperature and the mixture composition of the hot exhaust gas. So the can be calculated as initial pressure, ratio of change of molecules, and ratio of change of temperatures. And for most hydrocarbons we have a change in a factor of 7 with respect to temperature, which is the dominant factor here. So there's a rule of thumb concerning most hydrocarbons. So the explosion pressure we will have is around 10 times the initial pressure. So we are here, of course, then on the safe side. It also depends, of course, on the mixture composition. Normally slightly rich conditions. So here for methane, town gas, so methane, carbon monoxide, hydrogen mixtures, and here pure hydrogen. So you see within the flammability range, it again strongly depends on the mixture composition, which pressure we yield. Of course, the temperature alone depends strongly. Therefore, the pressure has to depend also. And of course, the combustion velocity, so the flame velocity we have seen already, depends on the mixture composition, and therefore the pressure rise, of course, also depends strongly on the mixture composition. There's one final effect here. So, and when I have my exams at the University of Braunschweig, this is always critical for the students. So it's an easy test if they have followed my lecture or they have slept at that time. What is the influence of volume? So if you have 1 liter, you have 1 cubic meter, you have 1 cubic centimeter concerning the explosion pressure. And there is nearly no influence. So of course, when we have really small volumes, we will see some cooling effects from the wall. But for hydrogen, this is far below 1 cubic centimeter. If we have 1 cubic centimeter of hydrogen, we yield nearly the same explosion pressure compared to a 20 cubic meter vessel. So this depends only on the chemistry, and the chemistry is always the same. So if we have the same initial conditions in these 3 different vessels, we will reach the same explosion pressure. But of course, the pressure rise strongly depends on the volume, because we start with a very small ignition volume, which then spherically propagates in our system, and the ratio burned to unburned gas is of course different in this large vessel compared to the small vessel. Just a sidekick here. This is what you normally find in literature, maximum explosion pressure. So that's the pressure measured when you ignite in a spherical sphere of 8 liters an homogeneous mixture. So as I've said, normally below 10 bar, so 7 to 8 bar is what we could expect. Of course, even without detonation, we can see different influences, and this is especially when have complex geometries like this here. So in the US, they use normally these so-called conduits. So all the electrical wires are in these conduits, and that for this market, you have to consider when you want to measure the maximum explosion pressure in a specific equipment, you have to consider the influence of such a conduit. That means you have to ignite it here. So you have a flame moving from here to here, reaching this configuration here. And of course, this is not an empty vessel, this is an electrical equipment. So there is something inside. And especially here, there is a separation between this part of the enclosure and this part of the enclosure. So following this US standard, you have to measure the pressure at different positions here, P1, P2, P3, and you have to measure this with different mixture compositions. And this is a specific US standard from UL, Underwriter Laboratories. This, of course, it's different in Europe, but it depends on this standard. So, and when we see here, we use acetylene with different mixture compositions. And normally 14% gives us more or less the maximum value. So slightly rich mixture. And you see here 14%. Okay, here this one has won the race, in this case 15.5%. So that's the P1 sensor, the one in the first chamber of the enclosure. So you see it here again. So here, in this configuration, we see what we would expect, that the maximum pressure can be measured with 14 plus minus something percent. And the other mixtures, then, okay, here we got lower values. But what is happening when we look at the next compartment of the enclosure? And first of all, we see that the maximum is now with 11%. And what is more interesting here, we reach a pressure of over 20 bar already. Again, we start at 1 bar and 20 degrees Celsius, leading here to 10 bar overpressure, something we would expect. And here, with just a few centimeters further, we already measure 20 bars, over 20 bars. So why is this happening? I have prepared here 2 videos. So here we have a large configuration. We ignite here in this compartment the mixture, and then here we have some orifices, especially here, and then we have here some mirrors. It's optically accessible from here, so we can see then the flame propagation after ignition here from the top and from the side. So we ignite on the right. You see now the flame propagation first, something like we would expect it, spherical flame propagation. Then the flame accelerates, and we create a large turbulent jet, which then ignites the mixture in our second vessel, which then leads to a much faster pressure rise. So this we can see here in this video too. Now we have a pipe, optically accessible. We have a disc here with an orifice. And the flame is coming from the left and going to the right. And you see here some some Schlieren videos of this process with 12% hydrogen air. You see here the flame is approaching, and you see how fast then this process occurred. So you have a pressure difference here. It's accelerated up to the velocity of the sound velocity of the head gas, depending on the configuration we have. And what you also see is, so it looks quite slow here. The flow comes with a given mixture, and how fast then the ignition occurs in this large, hot, very turbulent flow region. So, to explain you this more in detail, I have here one final configuration. So we have a tube set up, a disc with an orifice. We ignite on one side here, this I have explained to you yesterday. So in the chamber where we ignite, we see more or less the expected flame behavior. So pressure increases slowly with a function of time. And in the second chamber, when the flame reaches this chamber, due to this hot turbulent flow, we have a very fast pressure rise. That's the one factor. And we start not at 1 bar, because our flame in the first chamber led to a pressure rise, and therefore until the flame reaches the second chamber, there's a gas flow from chamber 1 to chamber 2, and here we start then with a higher initial pressure. So that means we have a fast pressure rise starting at lower initial pressure. For this configuration we already yield something like nearly 17 bar. And again, with the same configuration we also have measured 35 bar. So this is a very sensitive procedure, and therefore if you have to measure the explosion pressure in a complex geometry, it's first of all it's mandatory to do this because you cannot calculate it in advance, and second you have to perform some tests, and finally often get surprising results. So no one expects 40-50 bar in a simple geometry, but it can happen. And so the final value, you have seen the 3 pressure curves of propane, so 20 cubic meter, 1 cubic meter, 1 liter. So we yield always the same maximum explosion pressure, but there was of course different pressure rise. dP over dt was not identical, but often this assumption here works. So you normalize your dP dt max value of your pressure curve with the volume you have, with the cubic root of your volume, and this should give a constant number, so the kg value. This is sometimes tabulated, so kg for gases is not so important, but you can find it in literature, and again it's used to compare different gases. So the higher the kg value, the faster the pressure rise of this combustible, so the more dangerous it can be. This type of value is more prominent for dust explosions, which we'll see later on.